Okay then, so let us start. Uh, so in this session we'll be discussing about the hydroelectric power plant assignment. So that is assignment number 5, and I'm selecting a few questions which might be a little bit confusing to all, and other questions I found it should be well enough easy to solve. So these questions let us discuss these questions. Okay. So the first question, that was question number 4. It told us that means it was asking what should be the effective head at the Pelton wheel, and it gave the question told us about different kinds of heads, that is the total head, then um, HP is the penstock head loss. Then these are losses: nozzle head loss, bucket loss, and eddies respectively. So basically I would like to introduce you to eddies. What is eddies? So when we are looking at a laminar flow, so these are the particles will be moving in a constant same line, right? And each particles the previous particles will also follow the line that is followed by the previous particle, sorry, the next particle. Okay, that will move in the same line as the previous particle. So that is a laminar flow. But in a turbulent flow, the direction and the of these water molecules, these are not remaining constant. So that is not streamlined, and these are also accompanied by these currents that you can see. So these currents are basically called as the eddies, and these also, since we are not having any laminar streamline flow, so these are contributing to the losses in the flows. Hence these are eddies, and we know that before coming to the Pelton wheel, generally it is coming through the penstock, through the pipe, so there will be no such kind of turbulent situation. But when it strikes the bucket, so then the whole thing will change. Okay, as it is striking, it is no longer remaining streamlined, it is completely turbulent, and due to that the eddies will be forming. So that is after means striking the bucket. Then again we have the bucket losses, separate bucket losses due to the friction and the velocity boundary layers and everything. So these are bucket losses. So these two losses won't be contributing to the effective head on the Pelton wheel, because it is after striking the bucket, right? So before striking the bucket, what we have? The losses due to the penstock, at the penstock and at the nozzle. So at the penstock there will be some shear losses. Then in the nozzle, when it is coming out, so it we multiply with a factor CV, right? It is forming a vena cover. So like that, these are the losses which we need to consider to measure the effective head. Hence the answer should be B, that is the total head minus the penstock and the nozzle head losses. So next question was, so this is a very straightforward question as it looks, right? The specific speed, it is already given, and you're given all the variables here, but still I think maybe a few of you might have made a mistake because of a certain thing about the units. So the specific speed is given as n into this root p divided by h to the power 5 by 4, but n and h, these are in the known quantities, that is meter than rpm, but p, it is not in watts, it is rather in kilowatts. So if you do not multiply this 10 to the power 3, means convert it, sorry, this should be where it is given, this is 25 megawatts, right? So 25 megawatts converted to kilowatts, so 25 into 10 to the power 3. So if I convert it whole to watts, then I will get this last option, 3810. So this is a tricky question. Like that we will get ns to be 120. Is anyone having any doubt?
Yeah, Mr. Kanwar,
Yes, sir.
no, actually, regarding eddies are nothing but a circular motion of water only, right?
Right, sir.
So, so why there should exist a loss in eddies?
Huh, because you see that circular currents are being formed, and these circular currents are generally being formed after the wake, means after striking. So basically, the direction which was completely focused, the velocity direction which was completely focused previously over the bucket or to a particular direction, means to the nozzle. Now it is being separate, means it is deviating from the actual direction. So now it will be striking everywhere. You just imagine the water will be striking everywhere due to the eddies. There will be currents and it will be a chaos. It will completely chaos.
So
But
its momentum gets lost, yeah.
sorry,
So its momentum is getting lost, yeah.
momentum is getting focused in different directions. The momentum was the momentum should be conserved, right? It will be conserved, but the final momentum that we're having, it is being focused in all other directions, right? So
Okay, right.
that is why, since we are not getting a constant momentum, focused momentum at the final part, so there are certain losses.
So, so actually, in penstock, in nozzle, under only frictional loss is happening. That's why that loss is happening in penstock. That loss is happening in nozzle. We say that losses penstock loss or head nozzle loss. But actually, there occurs only frictional loss, right?
Exactly, exactly.
So similarly in
But
case of
there is one thing, sir. But if the flow is above the critical Reynolds number, then the flow is turbulent, and in turbulent flow, there might be some eddies, because there is a chaos will be formed. But generally, it is considered that the flow through the penstock through the nozzle, it is not the turbulent. It is laminar condition, so it is being assumed here.
mm-hmm. Okay, so in that case, the friction contributes to loss of energy, but in case of eddies, what contributes to the loss of energy?
The change in actually the force is being calculated as a change in momentum, right? The final momentum is a sum of the momentum of all the water molecules, if you can see from the molecular level perspective, right? So then you now imagine, first of all, the momentum of all the molecules were in the same direction. The velocity vector was in the same direction. Now the velocity vectors are being deviated from the constant direction, so the momentum is now dispersed and the total final momentum we are getting is less. So the change in momentum which contributes to the final force, okay, so that is coming out less.
Oh, okay, so that we say as loss, huh?
Because we are not getting the actual velocity force that we needed, and that force is actually needed to for the tangential movement of the blades, right? To move the blades.
Okay, okay, okay. Okay, sir. Thank you very much.
Okay, thank you. So the specific speed, so you should everyone should take care of this unit. This should be in kilowatt, and if the unit is correct, we will find it as 120. And later on, I will be also speaking about about another dimensionless form of this specific speed, that is shape number. So I will be talking later. Then there was one question. The Pelton wheel turbine bucket angle is 165 and the ratio of the peripheral velocity to jet velocity is 0.46. It is a very straightforward question. Simply the velocity ratio is given. Then we know the efficiency. So this is based on if we simplify it, so VW1 plus VW2, if we simplify it, it will be coming in terms of V1 and U. So we know that equation, right? So the mass mm is cancelled, and if we arrange it and simplify it, we will get this particular equation in terms of velocity ratio. So simply we put the equation, this theta value. The theta is the final deflection. The jet is deflected 165 degree. So we just put the value and we will get the final answer to be 97.67%. That is C. Then the next question, which was quite related, the maximum theoretical jet deflection angle of a Pelton turbine is reduced by 20 degrees. By what percentage does the efficiency reduce to? So first, looking at this question, many of us will be thinking that, okay, suppose there is one theta, which is the maximum deflection angle, and we reduce it theta minus 20. So in these two cases, what will be the reduction? That should be a general analysis, but actually here we are talking about the maximum theoretical jet deflection, and what if we reduce this angle by 20 degrees. So the maximum theoretical jet deflection is 180 degree, because if we arrange the turbine blades in such a way that the jet is reflected and at the opposite direction of the coming that is coming from the nozzle, then that is completely 180 degree, right? So that generally it is not done. The 165 degree that is being kept is because this jet should not directly hit the bucket which is in front of this bucket. Okay, there should be a provision made for the water to move out without hitting the bucket subsequent buckets. That is why this 165 degree is kept. But as we if we look at the equations of efficiency, okay, so the cos theta, cos 180 degree minus theta, so so if the theta is 180 degree, so that will be cos 0, which is 1. So we will get the maximum efficiency in that case, but we do not keep it as 180 degree because of this condition that the bucket at front, the water should not hit the bucket, it should freely move. That is why 165 degree is kept. Now our question suggests that if the condition is maximum theoretical deflection 180 degree, and if we reduce the theta to 160 degree, you can see, you can imagine from here, then what will be the reduction in efficiency? So the efficiency we calculate separately. The R is remaining constant at both the cases. Then the reduction in efficiency can be calculated in this manner. Okay, simple calculation. Okay, will directly get us 3%. So this is the reduction efficiency. The answer is D. Then hydraulic turbine, this is one related to the hydraulic turbine. So at a potential site for a this is completely easy, I think. At one potential site for a hydraulic plant, the gross head is 150 meter, and the estimated volumetric flow rate of water through each turbine would be 1.2. Ideal power production per turbine. Excuse me. So the ideal power production is, if there is no losses, the efficiency is 100%. So ideal power production is that. So simply mgh. So m can be splitted into rho into q. Q is the mass flow rate. Then we will get 1.77 megawatt. So this is our answer. So ideal power production, as we talked about the head losses, then under other losses, so all the whole of the kinetic energy of the water is being converted into work done without any losses. So that is called the ideal power production. Then, as I previously said about this specific speed, so there is another term related to the specific speed, that is the shape number. So the question states like this, that a hydraulic turbine is to be sited on a dam on a river. So the flow rate is given 1500 meter cube per hour. The available head is 24 meter. Okay, the turbine is to rotate. The speed is given 488 rpm, and the efficiency estimated is 89%. So let me talk about shape number. The shape number, so specific speed, it has units in rpm, but if we want to non-dimensionalize it, okay, then the quantity that we will get by introducing the density and the acceleration due to gravity is called as the shape number. So shape number is basically the non-dimensional form of the specific speed. So this is given as by this formula. So first we'll have to calculate the power. So power, this is actually eta. So eta is estimated to be 89%. So 0.8 into the whole total power, we got the power in kilowatt. Okay, so that when we multiply, so this is 0.154. But now there's one values, this no value here actually matches with this, right? So I think this C part should have been 1 5, not 5 1. So I will again communicate with the question makers to solve this issue, and I will send you the final answer regarding this.
Hello, sir.
Please.
Sir, actually, I also got that 0.154,
Hmm.
but based on options, I rounded off to 0.2 and I clicked on option D.
Hmm.
But it shows option C as correct.
Right, right. So actually, this is a bit of confusion. So I will have to get it clear from the people who have made this question, right? So I am communicating with them. I will soon. I will inform you about this answer, and also the subsequent this assignment questions also.
Yeah, actually, please ask them that 0.2 also will be right now. So by rounding off that.
Uh-huh. So I will ask and clarify this doubt.
Yeah, yeah.
Okay. Okay.
Excuse me, sir.
Please.
Sir, in exam also the questions will be like this only, or how the questions will arise, sir?
The
Like
questions.
how the assignments are given, like that, or like these few questions on shape number. These kinds of problems we are facing, no, sir. Like these type of questions also included in the exam, or what?
So the questions, I think it would be a little bit comprehensive. There would be one question, and related to it, a lot of this joining questions parts will be there. Like shape number is a very small thing to calculate here. But suppose you do not know the power or something, so there will be a lot of questions related to only one question, like that, a little bit parts, right? Like in question number 13 to 15, so it is based on one question, right? So something like that would come.
Okay, sir.
So
And by sir,
hmm.
assignment questions will repeat, or like
No, 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 no. And nothing will repeat. You cannot expect them to repeat, na. So you'll have to get prepared from these assignment questions. It would be somewhat similar to whatever is taught and the assignment questions. So basically, assignment questions, what I think is that it is not exactly related to what is being taught in the video. Rather, it is to for the students to explore more bit in the this field. Okay, so from this the shape number, maybe it was not taught in the video. So, but it is related to the specific speed which was told in the video. So like that, a few things was given in the assignment. So overall, assignment and the video together will constitute the whole syllabus and will make you prepare well for the exam. Okay, then let's move on. So as I already told that here I will be also talking about the Francis turbine and the Kaplan turbine. Okay, the how it exactly works and how it is different from the Pelton wheel. So Pelton wheel, the water jet, it strikes tangentially to the wheel, and that is why it is imparting the force, impulsing upon it the buckets. As a result, it is rotating the buckets. So it is a pure impulse turbine. But Francis turbine, these are actually impulse reaction turbine. Again, Kaplan turbine also. So again, Francis and Kaplan, these are a little bit different based on the flow direction. So what happens in a Francis turbine is that, so the water uh, so if we consider this picture right now, so here the water enters here and it will go through the this guide veins. So you see here, these are the guide veins, and as it goes, there is a in the radial direction it will enter into the runner blades. Okay, so you see here in this picture, so in the radial direction it is going to the runner blades, and the runner blades are so oriented or so designed that the entry of the jet is in radial direction, but the exit is in axial direction. Axial meaning the shaft longitudinal axis, along the shaft longitudinal axis. So I have actually a video which demonstrates how actually it is being working, an animation. So let us look at it. And before that, let me talk about this draft tube and this tail race, why it is being uh, means a draft tube is basically assembled to prevent the problem of cavitation. So somewhere the pressure will go below the this and means the pressure at which it will directly convert into gas, right? So then there will be huge pressure waves will be generated due to cavitation. As a result, it will damage the few of the components. It may damage. That is why the draft tube is given. The shroud ring, the shroud ring is this, you can see it is basically given to for the water to flow through this means give a direction to the water. So this is a direction for the only the direction purposes. Then let us uh, watch the video what is exactly happening in a Francis turbine. So this is a video which I have taken from the from YouTube. It is available in YouTube, and this is the source.
Francis turbines are the most preferred hydraulic turbines. It contributes about 60% of the global hydropower capacity, mainly because it can work efficiently under a wide range of operating conditions. Most important part of Francis turbine is its runner. It is fitted with a collection of complex shaped blades. In runner, water is entered radially and leaves axially. During the course of flow, water glides over runner blades.
So you can see the water, it comes in radially but it flows axially. You can see the direction as it is changing. And uh, okay, let's move.
Francis turbine blades are specially shaped. You can note that blades are having thin airfoil cross-section. So when water flows over it, a low pressure will be produced on one side and high pressure on the other side.
So for those who haven't attended any aerospace classes or in air are not familiar with the subject aerodynamics, what happens is that when this kind of shape that you see, so this basically is an aerofoil shape, and it creates a pressure difference on the means when the fluid flows. So basically you can take an example of the this wings of an airplane. So how it is shaped, right? So this is a similar kind of shape, and as a result there will be some force exerted upon this blade due to this pressure difference. So this is the reaction that it is being this blade is producing, and hence this kind of turbines are also called as impulse reaction. Now why impulse, we will look forward in this video.
This will result in a lift force. You can also note one more peculiar thing about the blade. It is having a bucket kind of shape towards the outlet. So water will hit and produce an impulse force before leaving the runner. Both impulse force and lift force will make the runner rotate. So Francis turbine is not a pure reaction turbine. A portion of force comes from impulse action also. Thus, as water flows over runner blades, both its kinetic and pressure energy will come down. Since flow is entering radially and leaves axially, they are also called mixed flow turbine.
So you now know that this is entering radially and coming out axially. So this is the category of mixed flow turbines, and these are both imparting the force from impulse and reaction, hence it is called as the impulse reaction turbine.
Runner is connected to generator via a shaft for electricity production. This arrangement is fitted inside a spiral casing. Flow is entered via an inlet nozzle. Flow rate of water will get reduced along length of casing, since water is drawn into the runner. But decreasing area of spiral casing will make sure that flow is entered to runner region almost at uniform velocity.
So here I would like to comment the scroll casing that you can see. It is of decreasing this area. As the water increases, this is having the higher largest area, and this is having the lowest area. Why? Because as it is coming inside the flow rate, it will the water will come inside these blades, right? The flow rate in this direction, it will decrease, but we need, our final goal is to have a constant velocity. Okay, so we know that this mass flow rate is equal to area into velocity, right? So the mass flow rate is decreasing, so if we also decrease the area, then we'll have a constant uniform velocity. So that is why this is designed in such a manner. Okay.
Stay vanes and guide vanes are fitted at entrance of runner. The basic purpose of them is to convert one part of pressure energy to kinetic energy. Flow which is coming from the casing meets stay vanes, they are fixed. Stay vanes steers the flow towards the runner section, thus it reduces swirl of inlet flow. Demand for power may vary over time. The guide vane mechanism is used to control water flow rate and make sure that power production is synchronized with power demand. Apart from controlling flow rate, guide vanes also control flow angle to inlet portion of runner blade. Thus, guide vanes make sure that inlet flow angle is at optimum angle of attack for maximum power extraction from fluid. Low pressure at exit side of turbine may cause serious problems of cavitation. So a carefully designed draft tube is fitted at exit side to discharge the fluid out. Draft tube will transform velocity head to static head due to its increasing area and will reduce effect of cavitation. Hope you had a nice session on working of Francis turbine. Thank you.
Okay, so this was the how a Francis turbine works. So the points which we need to note is that this is here the water flows in radially and comes out axially along the direction of this the longitudinal axis of this runner. Then hence it is also called as a mixed flow turbine. Again, there is an aerofoil. These runner blades are actually aerofoil, having aerofoil shape, which is imparting some part of this tangential force in terms of this due to the pressure difference, and hence this is called as the reaction. Okay, and some, as it is also having a dent towards the lower portion, so it is also causing impulse. So means the jet will be hitting the turbine just like a Pelton wheel, and due to the impulse it is rotating. So this is having both reaction contribution as well as impulse contribution, hence it is called as an impulse reaction turbine. Okay, and the draft tube, it is basically given to avoid the problems of this cavitation, and we will see how this turbine is basically different from other turbines like Kaplan turbine in the next slide that I'm showing.
Francis,
Okay,
Francis,
so next is the Kaplan turbine. So here I am showing you the schematic of a Kaplan turbine, which I have taken from the book Power Plant Engineering by P.K. Nog. And then here it is completely means most of it is similar to the Francis turbine, but one thing is different is that although the water enters radially, but it enters the runner blades which are present, which are attached to the this runner that you can see here. So the water enters into the through the runner blades in axial direction. Okay, we'll also see a video for this. I'm just stating a few points before that. So it flows, the flow is in axial direction, hence it is called as axial turbine. Again, you see the scroll casing, you see that the area, it is decreasing as the water is entering through here, the highest area is over here, and it is decreasing um, in the direction of the flow, because again, to maintain an uniform velocity. So the area, if it is decreasing, also the mass flow it is decreasing, so together it will constitute a constant uniform flow velocity. Then these are the guide vanes that you can see, and these are finally the runner blades, or also called as the runner vanes. So here there is one difference from the Francis turbine, is that these are actually pivoted, not welded to the runner. Okay, if it is welded, then it has no degree of freedom, it is just static, it cannot move. But according to the flow condition, whether it is low flow condition or high flow condition, so we can actually adjust the direction of the vane, so we can rotate the vanes about this longitudinal axis of the runner. So that is why it is pivoted, and hence it is also means able to able to control according to the load conditions. So that was the brief introduction, and let us see the video how it is working.
Kaplan turbines are suitable for power extraction when water energy is available at low head and high flow rate, which means they are suitable for operation when water is stored in a big reservoir at a relatively shallow altitude. In Kaplan turbine, flow is entered through a spiral casing. Decreasing area of casing makes sure that flow is entered to the central portion, almost at uniform velocity, throughout the perimeter. Water, after crossing the guide vanes, passes over the runner. Finally, it leaves through a draft tube. Most important part of Kaplan turbine is its runner. Cross-section of runner blade will have a curved shape. When water flows over it, it will induce a lift force due to airfoil effect. Tangential component of lift force will make the runner rotate. This rotation is transferred to a generator for electricity production. Kaplan turbines are axial flow machines, where absolute velocity of flow is parallel to axis of turbine. Water is precisely made to pass through runner blades, with help of a shroud. Power demand may fluctuate over time. A governing mechanism, which controls position of guide vanes, is used to control water flow rate. This can meet for varying power demand. Blades of Kaplan turbine are designed to operate under a wide range of operating conditions. A rotating blade experiences relative velocity of flow. The fundamental thing in blade design is relative velocity of fluid flow should be at optimum angle of attack at all cross sections. Even though absolute velocity is axial, relative velocity will be inclined depending upon blade velocity.
So what it here means is that this tip and this root, so the root is connected to this hub, you see, and the tip is to the further end of this blades. So as we move radially outwards from the hub, the speed of this blade will increase, right? So the speed in rpm is constant, but the at different diameter positions, the speed will be depending upon the diameter. So at here at the periphery it will be highest, and at the root it will be the lowest, corresponding to this blade. So accordingly we need the constant this optimum angle of attack at each position, but the blade angle is this changing. Hence the shape is so twisted or made like this that it is having an optimum angle of attack even with the change in the this blade velocity. So that is the purpose of designing the blades like this. And angle of attack means the this you can see the velocity and the angle between this coming velocity and this means okay, so it will be clear from the next part. So how the angle of attack is changing. So let us see.
Inclination of relative velocity increases as we move from root to tip due to increasing blade velocity. There should be continuous twist in blade from root to tip so that at every cross section the angle of attack is optimum. With varying flow condition, relative velocity will change drastically. Kaplan turbine blades are adjustable. When flow rate is high, relative velocity of flow will be more axial, so blade should pitch vertically. If flow rate is low, relative velocity of flow is more tangential, so blades are pitched in tangential direction. In short, pitching action of blade makes sure that blade is still in optimum angle of attack, even under varying flow. Apart from controlling the flow rate, guide vanes have got one more function. They help in controlling swirl of flow. If guide vanes were not present, the flow would be highly swirling in nature due to its tangential entry. Such a flow would reduce performance of turbine drastically due to its poor angle of attack. So guide vanes control swirl of flow for optimum angle of attack. Biggest challenge in design of Kaplan turbine is how to overcome problem of cavitation, which causes material erosion and
Okay, swirl of flow. Actually, that meant was that if the means the guide vanes are arranged in such a manner that it is having a tangential more component along the tangential direction, more component of the velocity in the tangential direction, so it will rotate or revolve around this axis, right? So it will not try to go inside into the means from the shroud, it won't try to go through this in the axial direction. So that to reduce that, this guide vanes have a very important significant contribution. So these the angles are so governed that, and there is a governing mechanism, there is a link, and this link by this particular link that you can see here, these are the angle are uh, the suitable angle is managed. So by this angle, the tangential component of this velocity, which imparts to the rotating effect around this longitudinal axis, that is reduced. Hence the water is more prone to go in axial direction. So that is the main one of the main contributions for this guide vanes.
vibration. Cavitation is unavoidable in Kaplan turbine, since in most of the regions, pressure goes very low. But damage due to cavitation can be reduced by using suitable blade material and use of anti-cavitation fin. Draft tube, which transforms dynamic pressure to static pressure due to its increasing area, also helps in reducing cavitation effect. Thank you. Hope you got a good understanding on Kaplan turbines.
So these were the this how the working conditions or animations regarding the working of this Kaplan and the Francis turbine. So the important things in a Kaplan turbine is the flow is in axial direction, and these are pure reaction turbine because the aerofoil shape, the shape of these runner blades are so arranged that there is no impulse of the jet. And just like the case of the Pelton wheel where it is completely impulse related, so here there is no such kind of impulse, and everything, the rotation of the blades, the whole amount of force is generated due to the pressure difference that is caused by the this runner blades. Now the runner blades are also having these are pivoted to the hub in order to measure means maintain a suitable angle of attack. Angle of attack means the fluid which is coming and hitting the this blades. So what is the angle of this fluid which is hitting the blades? That is the angle of attack, and it is depending upon the relative velocity also. So accordingly it was a little bit pitched. So that was about the Kaplan turbine. Now let us talk about the assignment problem which was given related to the Kaplan turbine. So here the question 13 to 15 is also related to the Kaplan turbine, and here you can see that the question states like this: the Kaplan turbine develops 1000 kilowatt under an effective head of 8 meter. The overall efficiency is 0.86, the speed ratio is 2, the flow ratio is 0.6, the hub diameter of the wheel is 0.35 times the outside diameter of the wheel. So we need to find the flow rate, the runner blade diameter. So actually it was given as the hub blade diameter, but there is no this answers which was means none of the answers were corresponding to the hub blade diameter. So one of the answer was actually matching to the runner blade diameter. I will again confirm this from the question makers, and I will but I think this should be the runner blade diameter. Then the third option is the speed of the turbine. We need to calculate all these parameters. So let us proceed. So first let us calculate the flow rate from the power that is being given. So this is the efficiency eta, and efficiency into this whole overall power that is being contributed from this water jet at the inlet of the nozzle. So this is will give us the power that we are producing, and we only do not know only one quantity, that is the flow rate. So from this we will get the flow rate like this. So 148.16 meter cube per second, that is the flow rate. Then we are given a flow ratio of 0.6. So flow ratio basically means the velocity of flow divided by the 2gh. If you look at the velocity diagram, so there is one this velocity of the blades, velocity of flow, absolute velocity. So actually I have not given the velocity diagram out here, maybe it would have been more clearer, but the velocity of flow, so that is contributing the axial thrust. Okay, so that this velocity flow divided by the actual absolute velocity coming out to the nozzle, so this is the flow ratio, and accordingly we have 7.52 meter per second. So velocity of flow is actually the velocity of the fluid which is moving through the cross section of the between the runner blades. So here you can see that these are the runner blades. So from here the velocity the fluid will be passing through this segment. So the velocity of the flow through this cross section is the vf1. Okay, so this we find out as 7.52 by simply calculating this. Then we know the flow rate, so basically then we can find out what is the area of the between the runner blades. So if we do not consider the thickness of the blades, so we will find that this whole runner blade is a circular. Okay, the area contributed by this runner blade is circular. So the area of the runner blades, since the flow rate is in this direction between the blades, and the velocity of flow between the blades is we are just calculated, so this will be the area between the blades, right? So at any cross section this will be the area like this. Then now we are not considering any thickness of these blades, so we will directly subtract the total area being provided for the flow. So this is the area of the hub. Through this the water will not flow, right, but only the water will flow through this between the blades. So that is the external diameter of these blades as d. So accordingly we will find this is the area that is available for the flow, and the diameter, external diameter or the runner diameter, will be 5.35 meter. So this is the runner blade diameter. That should be there should be one correction actually there, but I will again confirm them. Then next we will calculate the speed of the turbine. So for speed of the turbine we are also given a speed ratio 2. So the velocity of blade divided by the absolute velocity of the fluid, so that is 2, and the velocity of blade is 25.06 from here. After that we know this equation, that velocity of blade is pi d n by 60. We know the outer external diameter of the runner blades. So then from this we will get the speed at which it is rotating, that is 89.46 rpm. So these were the questions in the assignment 5, and we have learned about the working mechanism of the Francis and Kaplan turbine. So that was all for today's session. And is there any questions? Okay.
Sir, how many assignments consider for calculation of marks?
6 out of 8.
Sir, what is formula, sir, if I leave one assignment?
I think there won't be any issue, because the best 6 will be considered for calculating the assignment marks. So if you are not attending any one assignment, so basically you are losing the probability of getting the highest marks through assignment, right? So it would be in your favor to do the assignment, but again it's your choice.
Okay.
And as I have said, I will again ask the people who have made these questions, and I will clarify the doubts which we had during the other assignments. Also, I will be preparing the answer sheets as many of you have requested for complete solutions, and I will be sending them to you. It will take me some time, but I will be sending them soon. Okay, then I think we should end this session if we do not have any other questions.